that all of this quantum tech, quantum machine learning, quantum sensors, quantum computing, algorithms, internet security is going to go into neuroimaging in specific. Now, today's neuroimaging is actually pretty good. You have machine learning, and then you have, data-driven learning, model data. You have different hybrids of different things. You get accelerated reconstruction. We're on the right side here too. And then neural network layering, motion correction, MRI denoising. Those are some of the things. Now, it's important to keep in mind with all these things that, there's an understanding of what quantum is, from 2019. And basically with Google and Caltech and, Harvard with this new paper, relatively new this year, they're basically saying that the error in the quantum computer is not the main thing, and it could be overcome with these sensors and computing. Now, with any of these things, you want to overcome noise, and you want more qubits in any type of quantum system. But in specific with quantum sensing and quantum computing and quantum algorithms together is this is called quantum machine learning. And so quantum sensors have been presenting on last 5 weeks, and basically this is the whole thing with quantum diamond sensors. If you place, they're biocompatible. You can place them a lot closer to the skin. Measuring all frequencies, reducing readout noise. And an interesting thing is a thing called quantum imaging. Now, quantum imaging consists of quantum sensing, as we see here, and then also consists of subshot noise imaging, quantum ghost imaging, and another one called quantum lithography. Now, the quantum lithography hasn't fared quite as well. But say, for instance, the other three are doing very well, in specific, mostly sensing. But with ghost imaging and subshot noise, you're talking about separating photon pairs or particle pairs, these types of things, and they have different paths. So one could see the detector, the other one could see an object, and the one that didn't see the object can sense from the other photon because it's still entangled to it. And then in computing, there's been this 2023 National Science Foundation projection that we will have something a lot better than we will this year, which is very encouraging, especially with this article I'm going to share. And then also ion trap, which is maybe leading in the whole Nature articles, these types of things. Photonic advantage, this is Xanadu, 36 microseconds instead of 9,000 years. And AWS, their hybrid jobs, basically this is late last year, and it's basically saying you could send certain tasks up. So this is reference 28. And then as you send them up, you do most of it classically, the hard things you do quantumly. And then you'll hear companies such as NVIDIA with CODA. And then what CODA allows you to do is to do CPU, GPU, and now a quantum processing unit, QPU. So it's hard to tell exactly where it is with that because they say people keep signing up, but it's not like say as advanced as Amazon's quantum briquette. And a lot of these things will be kind of small. The first quantum computers that are reliable, they say these accelerators, a couple qubits, and integrating them with HPCs as well, or supercomputers, high performance computers. And it just goes with it, quantum algorithms, internet, and especially for medical data, you just can't chance it. The thing is called post-quantum cryptography. Now there's a Google spinoff called Sandbox AQ. And basically, these algorithms from NIST and NSA are going to allow you to run on just standard conventional hardware. So even though somebody's attacking with quantum, you can defend conventionally. And then finishing up on the right side here too. So this big article that I pulled a lot of these from is basically, it was a symposium in 21, and then they did this big paper because it was just, there were so many findings in it. So for image computing, you have brain atlases, you have ML quality assessment, whole brain segmentation, and there's just a lot of different open source things and programs, FiberWeb XDK, and this other neuro program, NeuroLines. And then the big thing is called Radionics Automation. Now, for those that came a little bit later, Ron had shared with us on Meetup is basically, he says signal acquisition data rendering and diagnosis will be key things that will benefit from for Alzheimer's disease. And radiomics automation is basically taking images, and it's more about having a predictive machine learning algorithm. So it's a huge thing. There's radiomics and neuroimaging. There's radiomics in other parts of medical as well. Now, the terms people use for this are interesting. So, you'll hear the terms, quantum machine learning, neuroimaging, maybe a little bit long, quantum ML, neuroimaging. And it'll probably, if the quantum effect is substantial, it may be given that ML and AI will just be baked into it in the form of just quantum neuroimaging, something like that. So with all of this, as you can see, is that you have neuroimaging formation, and then there's lots of things that aren't perfect in images. You have artifacts. Now, one of the other members, he said neuroimaging, this is Larry D. And then, neural networks are very helpful, and it's for correcting, coherent image structures, and then reconstruction. There, if you recall from the previous slide, this reconstruction basically in the imaging phase is key. And especially if you have these, thousands of acquired signals and large databases as well. Now, when doctors, I don't know the exact details, but basically these are used especially when there's an image in question. So figure spend more money, these types of things. And I'm not sure if it's just, for all of them or just specific ones, but it does a really good job. So it's conventional methods that we're talking about with machine learning. And then that's the whole goal with all these things is basically, fewer training examples, are needed. And then this one's really interesting is that, and this would still go for, say, hybrid systems, quantum AI or quantum conventional, crowdsourcing with non-expert human raters for a convolutional neural net improves accuracy. So you actually don't want the doctors to look at it because they have other knowledge, and in specific, this is to get better quality assessment, so faster, more accessible, more consistent. And then here's an example. So this ground truth, I believe, on the upper left-hand corner is the culmination of these technologies. And in specific, you have input, frequency, image. Now, the second row is just zooms. So it's the red boxes, as you can see. And then, so in the first row is basically where you say, you want ground truth, frequency, image. So it's basically pulling the technologies together to get clearer and clearer images conventionally. Now, MRI brain atlases, voxel, which is like a 3D pixel, regional fiber, and whole brain levels. And then you have also with these things, open source software. This FreeSurfer has been around for, I think, since 2000. So it's using machine learning, but the most, the one that's working the best in seconds is basically neural network-based segmentation. And then also this MP range for signal noise ratio efficiency is popular as well. Now, when I came across this in the paper, and it's a really long paper, it's a symposium, and they pull in probably, I don't know if it's hundreds of references, but basically it says it speaks very, very highly of this term called radiomics. Now, radiomics, the definition, they say, focuses on the extraction of pertinent quantitative imaging features, often followed by incorporation of these features into a predictive machine learning algorithm. So that's the whole thing is prognostication, which is basically prediction plus a time. And then you have other predictive effects. But the typical thing is you're using machine learning. This isn't, quantum-based, it's regular machine learning for most, if not all of these, diagnosis, prognostication, treatment response. And then another big thing is getting biomarkers. So biomarkers are really key in a lot of these things because, you say, oh, if we can detect this with imaging, that this might mean this in specific. So radiomics is hindered because it incorporates many things. So if you have image acquisition, pre-processing, segmentation, feature implementation, it'll be the same thing with quantum too. But basically in this, in this case, if any of those, aren't right, then your end result, your end prediction, your end prognostication or biomarkers isn't going to be, completely accurate. And that's one of the things, potentially with quantum sensing algorithms, computing, to overcome these things with entanglement, like extra power. And then machine learning for personalized interventional therapies. So this is the whole thing with precision medicine. And then you also have these kind of novel brain-based predictive models. And then for workflows, so these, if they say radiomics, it's like a whole kind of thing, from imaging to that. And specifically what it's doing is this predictive machine learning algorithm. Now, the FDA, this was an issue. Basically, machine learning content continuously updates, but the FDA is basically proposing that we need something new. So one of the key cases is quantitative imaging extraction of features, such as serving as biomarkers. And then, say for instance, for this QI, which is another kind of like a good buzzword to use in neuroimaging, needs a training algorithm, quantitative performance specs, and instruction. So there's companies looking to, create IP. So like I said before, there's always going to be a need for better and better security. And like I said, with post-quantum security, with all these things and quantum, neuroimaging, is that you always want to, so it's basically better at defending than other types of conventional hardware that, hardware approaches software, the whole kind of thing. So in specific, data needs to be de-identified. So what this means is that the patient's name, all these types of things that relate to the patient need to be removed without removing the necessary information of the actual sample. So that's a very key thing. And this is for secure cloud servers, backup protocols, experts, curation and maintenance, strict guidelines and training. It's a very important thing. And they actually went so far in the paper saying, if this isn't right, then it could, cost the whole industry over one breach, and hence enter quantum internet, quantum cybersecurity, these types of things. So clear intellectual property guidelines are needed for these models and algorithms. And this is just one of the things if you're operating business in this field. And then also it's important to include all subpopulations. People think differently in different parts of the country, in different studies. And then also a huge goal is basically moving from today's kind of generalized approach to get more realistic heterogeneous data sets. And in summary, so machine learning promises to improve early detection, prediction, and treatment of diseases. Quantum technologies may further improve the field in these areas as well. So we're going to transition here. So basically, this is the second paper. So this first paper was this big symposium on machine learning and neuroimaging. Now, this is a specific one to quantum. So this is, as it's in the lower right-hand corner on the next slide. So basically, this is getting quantum advantage with Google's original Sycamore processor in October 2019, and then this time using sensing an algorithm called quantum machine learning. So this is their quantum machine learning update. And basically the issue, and you can see on the left side where it says findings, is that the processors are relatively noisy. And as you can see here is that what they claim what happens is with sensing these three things, sensing, computing, algorithms, is that you're overcoming a lot of the noise. And the principal mechanism is these primary states of entanglement. So that's why it's so important. And basically the way it does this is instead of measuring right away, like a conventional computer, is it holds on to it, entangles other different, qubits, I believe these are qubits. And then due to that entanglement, you can figure out things a lot quicker, storing it in quantum memory, as opposed to just measuring it right away. So They say the authors in this, and you can see below, you have Caltech, Google, Harvard, and 6 others, is that they're first at exponential learning. So this, anytime you see machine, learning, it's typically synonymous with machine learning. And then the QML collects and entangles multiple copies of quantum probes. So basically, and we're on the second kind of column here too, the way it functions is after this, you ask it, you finally do measure it, and I believe it's classically, even though it's originally quantumly, which of these observables was larger. And like I said before, in the middle column here where it says principal component is part of the superpositioning with the highest probability. So like I said, quantum computers are very noisy relatively to, say, conventional computing, these types of things. So it's basically saying because of these quantum effects, like I said, the three, so sensing, computing, and algorithms, is that it's robust to its own noise. Now, of course, you don't want the noise and it'll catch up with itself, but basically, and I'll show you their findings. And then in the third column at the bottom, it's basically saying, quantum sensors convert quantum data directly to quantum memory for quantum computing. That's QML. And then on the fourth column here, second from the right, is the details. So basically, this processor that they weren't doing QML to begin with, it was just a specific task, has kind of been criticized a little bit. And this is somewhat redemption for this original article. Now, with anything, we want more qubits, less noise. And then the fourth on the bottom here and on the columns is the desire, and there's many desires with this and moving forward, especially in the medical field, is to have quantum sensors equipped with quantum processing interacting with the physical world. Now, quantum sensing on its own, you're talking about entanglement scales proportional to n. Okay, so this isn't square root of n. And, you need this, well, basically it's four things, but quantum sensing. So instead of storing it initially, it's doing interactions with our other qubits. Now, in the bottom right-hand corner, basically it says desire, better quantum sensor, everybody wants. And as I shared before, they're getting a lot better. They're in Nature articles. Better quantum memory, which is, a huge goal too, and the methods to transfer quantum states to a quantum computer as well. Now, here's their findings. So they're somewhat easy to interpret. So the diagram on the left that says Q took exponentially fewer experiments to reach 70% prediction accuracy. So on the bottom is n as the system size, so it goes 2, 4, 6, and then up it goes 10 to the 0, 10 to the 1, 10 to the 2. So it's not linear, but as you can see, the blue is Q and the blue is better. And then on the right, you have quantum system. Basically, this whole top row here with quantum enhancement is you're separating symmetry classes where in conventional they didn't. So what's behind all this is basically the paper was December 21 was the big paper, and it's really kind of hard to read, and I didn't, as far as the conclusions weren't too awesome, but this is coming from the Google, it's a post on their website, and this is June 2022. So, both pretty frequently. Now, the previous article talked about the importance of quantum sensors. So you have, these quantum diamond sensors, and I'm going to highlight 3 or 4 of these, which are really important, especially in neuroimaging. So on the left is basically, it's called the MIT paper. It was posted at MIT and they worked with other collaborators, but on the top you have, it's called fluorescence. So you're shining in green, and on the bottom you have red where it says readout. And then what they did is this Rabbi and CPMG are somewhat normal, their sequences, but the mixing allows for all frequencies to be detected. So the specific details I would really read into, but a lot of people have kind of resonated on this paper because, to use, biologically inert diamonds, just carbon, with some vacancies, to do all these things. and to do off frequencies, and other members of the discussion have thought pretty highly of it too. Now, the one on the right is very interesting. So it's basically, you see the diamond, and then these things are built up around it with, the green laser, and then measuring red that comes off of it. So the key thing with this is basically the noise. It's removing, it's quantum phase sensitive detection, and it's in Nature. So this paper on the right is in Nature. The paper on the left is not, but it's MIT. So this paper on the right is basically, they took the MLK sound clip and they removed the noise from the original clip. It's really kind of fascinating to see, basically the quantum mechanics is going on inside the diamond. So there's a nitrogen instead of a carbon. There's a vacancy. So that NV, vacancy, when you're shining the light on here and there's a microwave generator, you see MW sequence holding the quantum position, the up downs in the correct manner, you're getting very good hyperpolarization. So that's the whole key with these diamond quantum sensors. So as mentioned before, so these types of sensors are being used to, you'll have to see Abby Rayleigh or just Rayleigh by itself, breaking these limits of, conventional sensing technologies. So you'll hear the diffraction limit, these types of things, and that's basically subshot noise is going underneath that. And then this paper on the right is basically getting, having signal amplification to decrease readout noise. So just imagine as these things start to go into neuroimaging, that, whatever the name might be, quantum neuroimaging or certain parts of quantum radiomics, is, the amount of effect that it can have when we're talking about entanglement, neural networks combined. So a lot of these things, the whole AI, ML, DL, now would be like, the big thing is QML that's mostly being done in the labs. And then AI is more like the user-friendly term that ML falls under. So I shared this before, and it's such an awesome thing. So basically on the left here is you have two different photons. One goes to the object, one goes to mass. Now they're entangled. So these two red lines here, even though the one didn't see the object, they are entangled. Now this whole process hasn't been figured out, and it still produces a noisy, low resolution image. However, because of neural networks, it took this image on the left, noisy low res image, and into high res image on the right. Now, the problem that this has is in the reconstruction phase, it takes a lot of time, computationally demanding. And then in specific, it's potential that other different types of quantum technologies, sensing, these types of things could help get this original image even better. But like I said, like a neural network is helping it in this paper. Now, this paper on the right is very interesting. So subshot noise. So I've shared it with some members before, is basically you're looking at this rainbow, where it says to the left of reference, and it's a full rainbow. And then so basically what you want to do is one part of the top, photon pair, and these two are still entangled at this point, is going to see the sample, and the other one does not. It, bounces off a mirror, this bottom one. So this whole effect using subshot noise. So basically, shot noise is basically it's going below that, and the only way I believe that you could do that is with quantum imaging. So this is the whole quantum subshot noise imaging kind of thing. So a couple of basically shout outs here. QSD does a lot of this stuff with quantum imaging. So like I said, the 4 aspects of quantum imaging or quantum sensing. You have subshot noise. You have ghost imaging, all quantum, and then you have quantum lithography, which hasn't really taken off since I think around 2000. Now, the reason why all of this is important, and it actually shared from before, is that 46% of medical imaging, or the compound annual growth rate of medical imaging is 46%, which is huge. Quantum computing is like 36%. So this whole field is destined to take off. Now, what puts icing on the cake with that is they said neurology, all these brain experiments, are thought to be the most important key of medical imaging of this compounding growth rate. Now, this RBC paper basically says that medical imaging takes 30% of the world data volume, and it's going to grow at 36%, until I think 2025, 2026. Here's this image again. So like I said, it's basically, it's a guidepost. It makes sense when you're reading these other complex papers, and it's specifically trying to, influence the medical world. If you've missed previous decks, so these are all available in deck form and, the video presentation such as this one. So these go from September, all the way September 29th, for pretty much like a deck and presentation every week. And then just a very good overview of quantum and neuroscience, anything from quantum, neurochemistry to just a really good quantum outline, which has over 200 resources if you're just starting off in quantum. But these things are going to be tied together, right? Like the quantum effect, especially going through 2023. Now, the big problem that Chemical Q device is solving is today's machine learning neuroimaging allows for conventional, multi-contrast, multi-dimensional, and multimodal results. So these are not, especially as the quantum technologies are developing, they're, using conventional approaches with neural networks, machine learning, AI, and DL on, classical bits. So the solution with all this is basically quantum machine learning neuroimaging with quantum sensing, quantum computing, and quantum algorithms for better images. And also quantum radiomics for improved diagnosis, prediction, and biomarkers. So the mission statement for Chemical Q device is this: to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and/or resolution, leading to advanced prediction in neuroradiology for Alzheimer's disease. This includes quantum sensing algorithms and computing for MRI, PET scan, CT, neuroimaging techniques. Now, the ultimate goal, or something realistic, is developing these quantum-based solutions, utilizing medical doctors collaborating in research labs. So here's this again, and then very interested, so we're gonna bring on some more people here. And again, so the people filing in here is that this will be available on YouTube. So if you missed any of that, it's here. I'll also post the deck as well. And then interested in any feedback. Like I said, I get a number of kind of inquiries from Meetup as far as, the goal with all this is, even if you have quantum, neuroimaging or quantum AI neuroimaging or whatever it gets reduced down to, at the end of the day, is it has to have an application. So that application is actually Alzheimer's disease is well defined compared to other disorders, neurological disorders. So that's where all of this is heading, is basically getting better pictures and then using, quantum radiomics to get, your better prediction. And then, instead of machine learning prediction, now you're talking about quantum machine learning prediction as well. So again, so the people just filing in, if you missed part of the presentation, I'll have this up on YouTube. And then I am interested, so we're gonna stop share and have discussion on this as far as people that have medical background and people that have quantum, and basically kind of your input as far as, and how entanglement of, two different photon pairs and qubits will have on brain images and prediction. So we have returning guests here too. We have new guests too. Bahar, you can go ahead if you have any questions.
Hey, thank you for the presentation. It was awesome. Again, since it's related to imaging, I don't know if you can hear me. Since it's related to imaging, it's very close to my what overall I've been doing. I like one question in the chat that I saw, and I think that would be my question as well. Sorry, I forgot who wrote it, but it was that what is in quantum machine learning that is not in machine learning. So I think it's a um, I hope you don't mind. I mean, I hope you don't conclude that I wasn't listening from the beginning, but I want to say, for instance, is there any system that they checked it with? I mean, everything was the same except the part that with and without quantum, and we showed that it is better. For one system, have you ever seen such a thing?
Yeah, well, so this Google paper, so this paper in 2021, so it's Caltech, Google, and even AWS. Like I said, it's got, and I think it's got Harvard and then 6 others. So basically, it's a redemption paper from the original 2019 Google supremacy. This is the first ever case of quantum advantage. Now, I don't know if it's always the case that for quantum machine learning, you have to have quantum computer, quantum sensor, quantum algorithms. But for this specific paper, that's what they did. And then I guess to better picture it is the whole point in this is basically the quantum computers today are still noisy. And people either want to not have the noise or to correct the noise, which is quantum error correction. Now, in this specific case, is they're taking this information. So if it's, photons or qubits, and instead of just measuring it right away, classically, is in the quantum world, what gives it its kick is entanglement. So a bit or anything by itself can superposition from 0 to 1 or anywhere in between. Now, but if you have two particles or 2 photons or whatever, qubits, and they're entangling, this is what gives it the quantum advantage. So this term is they've kind of dialed back on advantage, or they dial back on supremacy, but because it's not always the case that you do have quantum supremacy. But yeah, that's the main takeaway is basically in somewhere these operations, instead of just measuring things, it's actually in that whole measurement process is that you can get more information faster using entanglement of one photon relating to another one. So the Google paper is worth checking out because, like I said, it just consolidates everything. It's a lot more readable. I actually read that first, then I read the main paper, which is 5-6 pages. The Google one is like a post. So I hope that helps. But yeah, typically when you're talking about QML or even quantum advantages, there's entanglement involved.
I see. So that's the main thing. Got it. Thank you.
Kevin, I just want to clarify a bit about that thing. The measurement of photons, does that mean it's not in the binary world anymore? It's like it can do like a float addition or multiplication directly with photon measurements. Is that what makes it faster? Sorry if it's like such a fundamental question.
Oh, yeah. So, and this goes for everybody too, is if you have a qubit, there's a couple phenomenon. So a qubit on its own can superposition it. And so that means it could be off or on. And instead of like a bit in the classical world, it can also be anywhere in between. So that's called superpositioning of a single qubit. Now, entanglement, which is the power that we're talking about in these articles, is when you have 2 of those, qubits, photons, whatever's entangled, and then they're sensing each other. And say, for instance, like in quantum ghost imaging, one might go one direction, sense the object, and the other one might go the other direction towards the detector. And because they know each other, is that there's advantage in the entanglement. So quantum's all about superpositioning and entanglement.
Does that mean that the atomic operations of a quantum computer are potentially more complex? Like it can do like maybe like a median blur or some computer vision stuff in the atomic level? Like it's because like when you do certain arithmetic operations, they're actually just bit operations, but it's like a primitive in the quantum world, and that's how I get it currently.
Yeah, and I'll bring on other kind of speakers here too. And then the one thing I wanted to add with that is there's different types of quantum hardware technologies. So the one that we're traditionally talking about is superpositioning, is is the IBM, Google, Rigetti, this, like the one that has to be super cold. You have ion trap, you have annealing, you have neutral atom. So they all operate a little bit, they all operate differently. So, as far as the other, on the atomic scale, typically in the quantum world, you're talking about subatomic particles, those types of things. And a lot of these, kind of like the quantum imaging thing, if you have an entangled photon pair, that's a common case with those two, subshot and ghost imaging, is that, they can still sense each other, but they can be so many miles or kilometers away even too. And that's the whole thing with, like, China's satellite. And actually, I wanted to add something too, is that Fermilab and Argonne National Lab, so this is part of Internet, they've already transferred both classical and quantum information at that same time. So that kind of shows that it's pretty much a consensus. Quantum won't take over the world. You're going to still have hybrids and, CPUs and GPUs, now QPUs. So does that answer your question?
Yeah, kind of. So it helps in the data transfer part. And I just wanted to understand, like, in terms of like CPU or like a big O notation, maybe. Yeah, does it actually help quantum computing? Does it actually do something different? Maybe it can do like a array search for just O of 1 because of all those superposition stuff.
Yeah, and again, I think the line is going to be very, like, indistinguishable, because even I've heard cases of QML using aspects of classical, and it's a very kind of like, like how CPUs and GPUs are hand in hand, that like your CPU will mean remain the brain, but then the QPU, quantum processing unit, will be more like a GPU. But yeah, as far as specific things, there may be cases where certain things are pure classical, remain classical, and then certain things that are pure quantum. It just depends, because you're talking about quantum mechanics, and that's the main thing, is quantum computers can do complex numbers, linear algebra, quantum mechanics, these types of things. So to solve problems faster, you want to see if they can take advantage of quantum mechanics math, as that's the key. Quantum mechanics is at the top. So
yeah, thanks, Kevin.
yeah, you're welcome. Did we have another question here?
Yes, please. Very quickly, I'm just wondering which one would be more interesting in your opinion, having quantum machine learning algorithms looking at a complex images that is taken by, normal cameras, basically. You can have 3D images, you can have, time series images, you can have many different kind of images, but, they would get, they can be presented in terms of, I don't know, tensor or so on and so forth, and calculation can get complex. So QML algorithm can come really handy. Would that be more interesting, or you were talking about quantum imaging and then, addressing such images by QML? If I was clear in my question, do you know what I mean?
A lot of these things just depends, because it's just a case by case. Say, for instance, like in quantum sensing, these sensors can pick up temperature, and especially mostly magnetic, and they, as far as the number of applications, electric, temperature, these types of things. So, like I was alluding to before, is basically somewhere along that line, it has to benefit from using quantum mechanics. So, say for instance, quantum computers on their own can't do real numbers. They just do whatever complex numbers. So it's really a case by case this. And like I said, as far as like quantum neuroimaging or calling it quantum AI, is you're still going to have classical components for these things. And it really just depends on those specific things, but we know for sure. So from quantum imaging before, sensing, ghost imaging, subshot noise, and then quantum lithography, that's all for imaging, and that's quantum, right? So just this year, the subshot noise, the articles I shared, the subshot noise and the ghost imaging, they probably saw, considerable breakthroughs, one in absorption, one with neural networks, right? So yeah, I can't really get any more specific.
Thank you. I that was a very clear answer. For the ghost imaging, would that sorry if I'm completely off. I'm just trying to understand what's going on. For the ghost imaging, can that be like sort of helpful for blind people to see? Would that be something that can be seeable in the future? Or?
I think the main application so far has been dark images. That's the main thing. And the biggest issue it has is in the image formation phases with reconstruction, i.e. reconstruction algorithms. And say, for instance, MIT posted a paper with medical image algorithms specifically for reconstruction. So a lot of these things are likely to be tied together. And, I wouldn't say out of any of them, like it's still an emerging field, even though we may have a practical computer next year, according to the first funder, NSF. They funded it in the early 1980s. So yeah, it just depends on, like it's just with any business, you're going to have cost, and then you're going to have, like how ready is this technology for it's quantum diamond sensing. Basically in 2009, they thought that you could take these and put them on tips of MRI probes, instead of a full MRI, just on like an end of a rod. And then in 2000, there was some development during that time, but I think the straw that broke the camel's back is in 2021 is they figured out the algorithm to measure fluorescence better. So the red light coming off, exactly what does it mean? And then in August, there's two big Nature papers, rat's heart, 10-fold better magnetic information read, because you can place it a lot closer. And then the other one is this QPSD, which I think that may be a big thing, because it's basically saying removal of noise, using this diamond sensor with surrounding components.
Thank you very much. The last question I want to ask is, I have been working in medical image analyzing for a while, and also I have a, paper published, not published, it's still in archive, but, using Penny Lane to basically transfer the information, classical information to quantum information, and then use the quantum algorithm to analyze it to see if it has any benefit. If I want to get more involved in quantum, basically neuroimaging, is there any kind of data set or any basically paper that is a good start for someone who is been working in computer vision field and medical image analyzing for a long time and is eager to get into this field?
Yeah, and I could, if you text me afterwards or DM me, I did a quantum timeline, and that gives you like from 1900s all the way through. So I think it's really the quickest way to learn quantum technologies within an hour. It's like really an hour and a quarter YouTube. Now the other stuff, I shared here with one of the slides. I don't know if you captured it, but it's going to be up too. And it's basically, all the quantum tech from sensors, hardware, you have internet, cybersecurity, algorithms, those links. So those resources are really important, because the ones I included in there in that slide, there's like 84 of them between, conventional neuroimaging and then quantum going into all this stuff, is that they're very important, So as far as this field, quantum neuroimaging or quantum radiomics, I haven't found too much on it. So, it's kind of the thing, it takes imagination. Because you're looking at all these technologies and say, for instance, like the QPSD, noise reduction, quantum sensor, and then saying, okay, now I have noise reduction on hand. What needs that? Because I know for sure in today's machine learning neuroimaging, state of the art, is it could actually start reading the noise if it's fitting too well. So then if you can remove noise, those types of things. But yeah, it's a puzzle, right? Because I don't think there's really any books out there. It's just a bunch of quantum articles, and like I said, that one slide that I included here, and it includes kind of like the hot areas, and it was like this ML symposium for neuroimaging.
Thank you so much. I will send you a message later to get the link to the YouTube, and if possible, also, a copy of your presentation today. Thank you so much, Kevin, for everything. I appreciate it.
Yeah, you're welcome. And then, so Ron, go ahead, or Ron or Tony, either or.
I just wanted to comment on what, pardon me if I pronounce your name wrong, Azada.
That's correct, Azada, yeah.
If you're working in medical imaging and you're working with Penny Lane and selecting quantum algorithms, I think you're pretty high up the stack. You're well beyond what the position, what most people are having understanding of. I would be fascinating to hear a talk by you on exactly what some of those processes are that you're doing. It's everything that's going on in quantum is new. You may be finding yourself as a pioneer, so maybe you're the one that needs to write the book.
Thanks, Ron, for the kind words. I still really need to learn a lot more, but thank you. I really appreciate your kind words. Thank you.
You're very welcome. And again, I would love to have you come back either here with Kevin's group and talk about exactly what you're doing in that area. I think it'd be pretty fascinating. So some of the questions I heard tonight, just real quickly. QML is, for the most part, a hybrid system. Quantum is used for a piece of the machine learning puzzle, and it can be used at all various stages in the process, whether in the beginning where you have to train a model, it can be used to accelerate training. It can also be I believe to a lesser extent, it can be used to enhance running the model, although I don't think running the model is really a huge issue these days. But the thing about a lot of these words are beginning to flow together across this whole stack that Kevin presented tonight. Quantum can probably find places to assist every step in that tree, and but it's not going to do it by itself based on what we have right now. So there was a question about QML versus ML. Well, quantum is just an enhancement. It's still ML under the hood, but you can use quantum where quantum advantage will speed up the process. The other thing that I wanted to bring up, somebody asked a question about bits. People need to understand that a quantum computer, and actually the more I think about this day, calling it a quantum computer is really an unfortunate term. A quantum register or a quantum computer that has a register or has X number of bits that you can play with, they struggle to do basic math. They don't do long division. There's a whole bunch of crap that they just don't do. What they do is allow you to take a big chunk of data, encode it as a quantum state, and then work on it, work on that quantum state as a single operation. So when you're looking at a quantum register, let's say if you have 4 bits, that's 16 possible states. So whenever you do an operation on it, you're doing the operation on all 16 of those states simultaneously. And it just, so it's to try to map a lot of that to the classical bits where you know how to build. If you're into classical bits, you know how to build an adder. You know how to turn adders into multipliers and dividers. You know how to take bits and make letters. You know how to take bits and make numbers and floating points and stuff like that. None of that really works in quantum, but quantum has this ability. Again, you have to translate the data into quantum states and then work on it in the quantum states. And then when you read it back out, you're going to be sending the readout back, probably back to a classical machine for final analysis, for the most part. I think that's where we're at these days.
Yeah, that's awesome. So one thing I wanted to add is basically the reason why people are gaga over quantum computing is when you add a qubit, like 50 to 51 qubits, you're essentially doubling your information, as opposed to classical, it's more like a linear, it's just like a regular thing. So on classical hardware, we have Moore's law potentially coming to an end or slowing. That's the whole thing, is that theoretically, if it all worked with high qubits and low noise, is that you're in a really good spot for specific problems, right? And like Ron said, like we're talking hybrid still, a classical and quantum and other parts too. The other thing is quantum computing is really good for random numbers. It's technically it's probabilistic, not deterministic. So when you do Amazon Braket, their cloud service, and you run experiments, you run a bunch of them. So you have a task, and then you do so many shots, and then you can do whatever you want with the shots, maybe average, whatever. But it's again, like, I think a lot of people think that it's a one-for-one substitution, when in reality it's, it will likely have killer apps, but it's for specific things. And I believe that you'll see emerging stuff in quantum memory and quantum sensors, and they're actually using these quantum diamond sensors as qubits in quantum computers. So there's all these potential kind of things. So I never like that statement, like quantum computers will never, because there's there's so many other things that can affect that could be put into a quantum computer, and now it does, right? Any other questions?
Yeah, I had a question. And sorry if this was asked earlier. But have we as a community identified like certain quantum computers are better at certain computational applications than others? For instance, like, is there any for like QML neuroimaging, for instance? Are you aware of any difference in computational power or anything between like a trapped ion quantum computer or a superconducting quantum computer? Or are they pretty much considered level at this point?
Their architectures are all completely different. So Rigetti, Google, and who's the other one? IBM. They have gate-based superconducting qubits that take millikelvin temperatures, and IBM just up or downed on their a dilution refrigerator, getting it even colder to get better superconductivity, less noise, these types of things. So a lot of these things, like the article I shared today, this is on the Google gate-based superconducting qubit, and then this is the one from October 19. It's that processor. I don't know if it's that same exact quantum computer, but they're saying due to using QML, with quantum sensing and quantum algorithms, that this noisiest of technologies, gate-based superconducting qubits, the noise isn't the principal component, and I think it's more like the entanglement of the states. So, yeah, I think I haven't seen QML and ion trap. As far as like a physicist's dream, it's always the gate-based superconducting qubit with block spheres and all these types of things. And then you have neutral atom. I haven't heard too much from them. Quantum annealing, probably not.
You mentioned neutral atom. I just a week or so ago sat in and was able to converse with the lady, the lady who's the head quantum physicist there, about what they're doing. And I got to tell you guys, those neutral atoms are incredibly fascinating. I think I hate to be predictive, but they may be the golden egg in a couple of years.
Are they gate-based?
No, it's the most bizarre technology. They basically balance big heavy atoms on the pinpoint of a laser, and they're just held in space and operated on in space. It's not it's around beryllium. It's before or after beryllium. Beryllium, or I can't think of the name of it.
Is it like the strontium one or
strontium? Maybe, yeah.
Yeah. What? Yeah.
So strontium is a really, it's not technically inert, but it's a real stable atom apparently, and so it's not since it doesn't like to react with things, and unless you put energy into it, it should be, its noise profile should be much lower than all these other technologies. I'm not really sure what's holding them back, but their stuff, they're playing with two-dimensional planes of these things, and there's no reason they can't go to a higher dimension. So this thing could scale crazily. She didn't really want to share too much about what their major challenges are, but the whole their work is based on some work that was done by a Nobel laureate. He was the one who discovered that you could trap strontium atoms at the end of a laser, a focused, like a needle point of a laser. And we're talking about a needle point that's sharpened to like nano picometers or something like that. But it's just energy that somehow convinces that atom to stay right there, and it's in a complete vacuum. But then they use this whole array of these laser, they call them optical tweezers. I think laser needle is a better one, but they could put they got a grid of they're working with two-dimensional grids. I think they're up to 25 now, so it's a 5x5 grid, and they can get these atoms to interact with each other just by moving them in space. They can just move the laser. The other thing they can do is they can target two neutral atoms that they want to interact with each other, pulse them with the right energies, and they will do their thing. They'll entangle, they will Hadamard, or they'll do whatever they want them to do at the quantum level. It's just unbelievable. I'm just surprised it hasn't really accelerated faster than it has, but it's fascinating work.
Yeah, and one thing to add is basically a lot of these can be separated is if they're gate-based, like gate-based superconducting qubits, ion trap. I think those are the only two. But on the flip side, it's kind of like an established, like a known thing. Is basically it's not the hardware technology that is theoretically the best, which obviously the gate-based superconducting qubit might fall in that. It's the one that'll scale. So even if you have so all the programming and stuff, as far as I know, the bulk of it is on gate-based hardware. So I guess in that respect, like the quantum annealers and your neutral atoms, these types of things, might not have that advantage. However, if they have a breakthrough and they're the only one that can get to, say we're only like at 216 right now, I think IBM's due for 400 by the end of this year. If they have a breakthrough and they get 10,000, and actually psi-quantum photonics, I don't think photonics is gate-based. But basically, if you have breakthroughs in these other ones, that may trump, this whole KISS-kit, advantage, with gate-based. So I will say that, like, some of these technologies, like if you want to do simulation, like simulation of the brain, for better understanding of Alzheimer's, these types of things, I'm not quite sure. The model and the whole thing that's theoretically the best and will be the best also has the most error. So that's the whole gate-based superconducting qubit as well. So it's multiple things, right? So, in the papers, it looks like in Nature, IonQ, Quantinium, the ion trap technology appears to have the best handle on doing experiments and stuff like that actually have some meaning, like better meaning. But yeah, it's just a race. They're spin qubits. I don't know if someone's here, but like they're up to 6 qubits on spin qubits, and these are semiconductor. So these come off the line of existing semiconductor, you know, plants in the U.S. or China or anywhere. And these, you know, basically, since they're you know, they're silicon based, so it doesn't take fanciness in other areas like other technologies and quantum require. The last I heard, it still takes, I think, 1 Kelvin. So that's 100 times warmer than a millikelvin, which is what IBM Rigetti are at right now. So there's multiple things, but yeah, I think the biggest thing is just the one that scales, because nobody wants 200 qubits or 400 to do anything kind of pharmaceutical, and especially when you get up into simulating actual experiments inside quantum computers. You're talking millions. Like to display caffeine, it's 162 qubits to display caffeine inside a quantum computer, and we're at like 216, and that's just caffeine. So again, for those that have asked, is basically it's the whole perspective of this enormous potential if we get to really low noise and high qubits, that they can do things, doubling information from qubit to qubit size, like one more qubit, double information. So, and even penicillin, you're talking closer to the order of the magnitude of the number of atoms in the universe. It would, you know, that's the amount of information. So, but yeah, any other last questions we have here? If not, I just want to thank everybody for joining. Obviously, this is the big push for chemical Q device going into Alzheimer's. We actually have a walk down here in San Diego on Saturday, so I'm going to do that. And yeah, it's just an exciting time. Like, it's just, this is the time. We're in October. Other experts said 2023 for quantum. So right now it's really figuring out the papers and the area you want to go into, you know, in medicine or in whatever, and then seeing the quantum technologies that can fit. And then it's just like with anything, it's an exciting time. So I hope everybody shares that too. Anything else? Awesome. Yeah, I appreciate it, everybody. Have a good rest of your day. Have a great upcoming weekend. Take care. Bye.